Games are inherently complex. Dozens or even hundreds of objects can perform various interactions with each other in every frame. Managing all those interactions and tracking them can be a tricky task. In this video, we will take a deep dive into techniques that games use to store references between objects or entities, which is another term for the same thing. I will use a simple simulation example to better articulate the pros and cons of different approaches. Let's set up rules for our simulation. At any moment in the game's scene, candy can be spawned. Once spawned, they start to move in a random direction. There are also skeletons that spawn in random quantity at the game's start. They find the candy that is closest to them and chase this candy until it's either collected by them or a different skeleton. When this happens, they start chasing another candy that is closest. If there are no more sweets to collect, they start moving randomly. And these are all the rules we need for our simulation. Now, what kind of objects do we need in simulation to keep track of everything that's going on? This will be skeleton, candy, skeleton list, and candy list. Skeletons can have properties like position and target candy, which they are currently chasing. There are probably also other properties like velocity or animation state, but for this example this is not significant, so we'll leave them out. Candies will have only position property. The skeleton list and candy list will have a length property, which tells how many entities they store and objects themselves. What that means exactly I will explain in a second. Each of those objects has to be stored somewhere, they don't exist in the void. For your computer, it would be its memory. Each of the properties we assign to objects takes some amount of this memory. For position, it could be 8 bytes. For target candy, stored skeletons and candies, it will also be 8 bytes, and let's say that list's length will be 4 bytes. For the sake of simplicity, let's assume that lists can store 4 objects at most. This gives us the amount of space each type of object takes up in memory. The layout of items from this scene in memory can look somewhat like this. Now some facts about putting objects into memory or allocating them in another form. Those dots between objects are not a mistake. Even when allocating memory in sequence, we can't be sure that all items will lie next to each other. Memory that was allocated has to be eventually freed, either by the program shutting down or manually. But if a lot of memory is being allocated and never released, program runs at risk of running out of memory and crashing. The chance that this happens grows the longer the program runs. Each byte in memory has its own address, which is just a number. On a 32-bit system, it's a 4-byte number, which gives us 4 GB of address space, and on 64-byte system, it's 8-byte number, which results in a theoretical 16 exabytes of address space. Yet, for practical reasons, for the entities we are discussing, only the address of the first byte is important, as the layout and size of those objects are known at compile time, meaning that a property's position in memory relative to the first object's byte is consistent between different instances of the same object type. Let's now simplify this scene a little and replace property names with their value. We have 2 skeletons, candy, and 2 lists for each of the entity types. Each of the objects is located somewhere in memory. For clarity, let's just name addresses with letters. Position will be just x and y coordinates in the simulation space. The skeleton's target candy will be the address of the chased entity in memory. Such an address is referred to as pointer to candy. It can have 0 value in a situation where the given skeleton is not chasing any candy. The list length will also be just a number. Items will also be pointers. Thanks to such a design, whenever a candy has moved, the skeleton does not have to be notified about this in any way, as it always uses the actual version of every chased candy. To summarize, the whole process starts with skeletons being allocated. Pointers obtained during skeleton allocation are added to the skeleton list, then at any moment a candy can be allocated, and the pointer to memory it occupies is added to the candy list. Now skeletons code each frame, look through the candy list and detect that the new candy has been added. Both skeletons start to follow the same candy as only one exists. When one of them finally gets close enough, the candy is removed. This is where the first issues with such a design come to light, because what exactly are we expecting to happen at this moment? The skeleton that caught candy should set target candy to 0 or null. For sure, the pointer to candy should be removed from the candy list. Also, at some point, memory occupied by candy should be released. if we don't want to run into allocation errors later in the program's lifetime. But how exactly are all the other skeletons going to be notified that they should no longer chase candy? In the current situation, the other skeleton will still be going to the place where the candy was before it was released, as the allocation of objects does not invalidate the memory they occupied. But at some point, a chunk of memory that was used by candy will be reused by something else, something that may or may not make sense in the current context. This is basically a non-deterministic situation and an obvious bug in the code. What could be the first ideas that come to mind? Let's backtrack to the moment when candy was still in memory. Maybe we could add something like isActive flag to its specification. Then we can separate logic in three processes. The first is responsible for updating skeletons and checking if they have collected any candy. This process is responsible for setting the isActive flag from true to false if candy was collected. The second process, for each skeleton in which target candy is not active, sets it to null. The last process removes candy from the list and releases memory occupied by each inactive candy. This approach will work, but unfortunately it can be very bug-prone and hard to extend if game logic were to become more complex. The developer has to remember to check each time when dealing with candy entities if they are active. Also, processes have to be run in particular order. This is really hard to maintain, and I say this from experience working on Pumpkin Man, where I started with using this approach and then had to change it later, which fortunately wasn't too difficult. The second approach I could think of is to nullify all target candy for skeletons which chase given candy just when it's collected and before its release. This is a bit of a better approach as everything happens in a single procedure and no additional state is needed. The problem is that it's also quite hard to extend. If we imagine that there is another type of object that can keep references to candy, then we have to nullify those references too. Those references can become really hard to follow and to think of. And again, if we just forgot to set those pointers to null, we will run into hard to debug issues, because it won't be immediately obvious that there is an issue. In the ideal solution, we shouldn't be able to even run into this kind of bug. Now I will get a bit too technical, but in some languages there are systemic solutions to this kind of issue. For example, garbage collection in C# will make sure that memory won't be reused as long as something is keeping reference to it. Or smart pointers in C++, they solve a similar problem. But those systemic solutions, in my opinion, only move the problem somewhere else. For example, with garbage collection, it's possible to produce a state in which a single entity, the skeleton in our example, keeps candy alive, and we don't have any other reference to it. This is basically the same issue as with hanging pointers. It's only marginally better because now we know that memory won't be reused. What's worse, it may be even harder to spot that there is an issue with our code. With our simulation, what we need to understand is that right now we are basically keeping information about existing candies in two different places, and it's hard to keep this information in sync. The first is the candy list, and the second skeletons target candies. We need to change the way in which skeletons reference candies so that those references are immediately invalidated right at the moment when a candy reference is removed from the list. The easiest way to do that is to add new property to candy. Let's name this property ID. Each time a new candy is created, we assign a unique number to this property. Now, in skeleton objects, instead of keeping pointers, we keep IDs of candies. And what does that change? Well, each time a skeleton update is called, it has to look through the candy list to find a specific candy by its ID. If such candy isn't found, it means that it has been removed before, by being collected. By adding this layer of indirection, logic, which uses references to float candy, is forced to check if this candy is still prevalent. There is no way to make a mistake here. What are drawbacks? For sure, performance, because right now, each time you want to get a referenced object, we must first search for it. This can be mitigated by using something like a hash set, which I won't go into in this video. But let's go a little further with this example. Right now, it assumes that each time a new candy is created in a simulation, it allocates a new chunk of memory, and later this memory is released when the object is destroyed. There is an issue with that, as allocating memory is considered a performance-intensive operation, especially if we imagine that there are hundreds of objects created and destroyed each second. It's ideal to minimize the number of allocations and deallocations. What games often do is use something called an object pool. It basically means that the whole memory required for objects is allocated once in a single block at the start of the game, and then objects from this memory block are reused. This requires some extra logic, but is relatively simple to implement and easily separable. These object pools will typically have operations like make and free, which can be used to obtain and release objects back to the pool. Using pools reveals another opportunity for performance improvement. As all items are allocated in a single block, we can start to reference them by their index, which is just a number telling us which object in block it is. Now, only a pointer to the first entity is needed, as addresses for all other items can be calculated as the index and object memory footprint are known. This is probably where we should stop, but let's over-engineer a little to the approach that I am using. When an object is created with a pools make method, it's easy to return the index of the just obtained instance. It's tempting to use this index as accessing items through it is fast. It would solve the problem of searching objects by their IDs, yet at first glance there does not seem to be an easy way to use those indexes. If we just replace candy's IDs with candy's indexes in the skeleton structure, then there is no way for the skeleton to know if a given candy is on the candy list or not. We run into similar problems as with the first approach. There's one trick that we can use to get what we want. Skeleton object can hold both candy index and candy ID. Now, when the skeleton wants to check if the given reference is still valid, it simply uses the index to obtain a pointer to the candy it's following. Now, the make method inside the pool should assign a unique ID to the generated candies, and the free method should set it to some invalid value, for example 0. So, if the candy that is followed by the skeleton was freed or reused before, the ID that is stored in the skeleton will be different from the ID that is in the object behind the pointer. This way, it's certain that the object is not valid anymore and the references should be cleared. This way, with just one additional check, we can have both a really fast object lookup with the use of index and object lifetime logic which does not produce side effects. And that's all for today's video. I hope you learned something from this and found this topic interesting. Subscribe for more and leave a comment if you have any questions. Check out a demo of my game Pumpkin Man on Steam, and I'll be back with a new video as soon as possible. Have a nice day.